Okay, so another type of these limit problems is when you're given a piecewise function here, and there's absolutely no need to be able to know what the graph of this thing looks like in order to be able to do one of these problems well, but I wanted to show you the graph so that you can kind of see what's going on, and that way when we do another problem on the next slide, you can see how you do it without having a picture of the graph. So anyway, when they are asking about these limits as x approaches -4 here, the little superscript minus means what's happening with this function as x approaches -4 from the left side. So that means if here's -4, we're talking about from over on this side. So first of all, 2x plus 1, I show it with the little red squiggly here, that's this graph, which happens for all the x's that are less than -4. Absolute value of x minus 2 for x's between -4 and 3, that's the blue, which is this V-shaped absolute value graph. And then for x's that are bigger than 3, we've got this upside down parabola, 10 minus x squared. So the graph, the function does this. It comes up here, and then once it gets for all the x's that are less than -4, it follows this line. So it comes up and follows this line. Then as soon as x becomes -4, it jumps up here, it follows this blue thing, and then at x equals 3, it comes in here. And the way I knew that these, where these parts of the graph would be, was say, okay, well, if x was -4 in this function, plug in a -4 there, and you get 2 times -4, which is -8, plus 1 is -7. So that's why this thing finishes off at -7. It has an open circle there because it does not include the fact that x, it doesn't include -4 for x. It gets right up close to it, but doesn't include it. Then the blue stuff, if you plug -4 into this absolute value, you get 4. 4 minus 2 is 2. So that's why this guy would have a y value at 2 right there. And then it's going to follow what the absolute value looks like until it gets to 3. And if you plug a 3 in there, the absolute value of 3 minus 2 is 1. So this y value over here would be a y value of 1. So maybe 1 is there, and that's the height of that thing. So lastly, 10 minus x squared, which it does for x is greater than 3. Notice when you plug 3 in here, 3 squared is 9, 10 minus 9 is 1. So this guy leaves off at a y value of 1, and this guy picks up at a y value of 1. So it's interesting that those guys meet there, but they don't meet over here, and that's going to be a big thing in this problem. So when you're asked what the limit is as x approaches -4 from the left, all you need to know is that we're talking about -4 from the left means values of x that are less than 4. So you go find the part of the rule that says what are x's that are less than 4, -4. So that's these guys. So you plug in -4 here, you get 2 times -4 plus 1, which is -7. So that is 2 times -4 plus 1, which is -7. Don't worry about the fact that this is less than -4. It doesn't include -4 because this is asking what's happening as x gets close to -4 from the left side. So being less than -4 means that we're allowed to get really, really close to -4. So all you do is you plug in -4 into that part of the graph, or that part of the function. Now if you want -4 from the right side, you're talking about this stuff, you just plug -4 into the stuff where x is greater than -4. So when you plug a -4 in there, the absolute value of -4 plus 2, or I'm sorry, minus 2 minus a 2 is 2. And so that's that limit. Now, the only way to decide what the two-sided limit is, is when it says x approaching -4. That means you have to consider what's happening from the left of -4 and what's happening from the right of -4. If these two numbers aren't equal, then our answer is does not exist. Limit does not exist because the left side doesn't equal the right side. So we'll go over and see what happens at 3. To the left of 3, the limit as x approaches 3 from the left. That's x's that are less than 3, so you plug a 3 into the absolute value of 3, which is 3, and 3 minus 2 is 1. So that limit's going to be the absolute value of 3 minus 2, which is 1. And so if we're looking at the right of 3, which is here, what happens is x goes to 3 from the right side. We just have to plug in x's that are greater than 3, so we're going to use this function, 10 minus 3 squared, which is 10 minus 9, which is 1. Because these are both the same, that means the two-sided limit is also 1. All right, so we just have to put a little equals 1 there. So all you're looking for are these two-sided limits. When it doesn't have a little superscript up here, you just say, is the left the same as the right? And if it is, it's 1. If they're not the same, then it's a DNE. So we have, a sample problem I just made up here. Again, it's a piecewise function. It has 3 pieces to it. Really common for these kind of things. So I just want to run through this quickly to make sure that we've got it before you go on to some of these other problem types. So for the limit as x approaches 1 from the left side, we're talking about x's that are less than 1. Yeah, maybe think of a number line here. Here's 1, here's 3. So x's that are less than 1 is over here. So we're thinking about x's that are less than 1. We're talking about plugging 1 in for this x. So 3 times 1 minus 2 is 1. All you need to do. Now, if we want x's to the right of 1, talking about this stuff, so we look for x's that are bigger than 1. We plug the 1 in here. I call the 1 I would call it a border point because it's kind of the border between this function and this one. And when you plug 1 in there, you literally just get 1 for that x. Notice that these are the same. So the limit from the left is 1, and the limit from the right is 1. So that means the two-sided limit is 1. So you never really answer this question without answering these two guys first. So now when we go over here and see what's happening to, as x approaches 3 from the left side, we're talking about what's happening in here. We look for x's that are less than 3, and that's just given by y equals x, so it's just 3. And then we look at, see what's happening as x approaches 3 from the right side. Those are x's greater than 3, and when you plug a 3 in here, you get 3 plus 1, which is 4. See how these are not the same? What does that mean for our two-sided limit? When these two guys aren't the same, it means DNE. Okay, so time to learn a little vocab and deal with a question like this. Again, a really, really common type of limit problem. It's really not that hard. There's some vocab here that you have to get used to. But other than that, it's pretty straightforward. The only thing that's going to stink is you need to be able to factor. So when they ask you, find all points of discontinuity, I want you to just translate that into what x values make the denominator equal 0. Because that's really the thing in math, is you can't have a 0 in a denominator because it means you're dividing by 0. So when they say find all points of discontinuity, what they really say is, just tell me what x values would make the denominator 0. But in order to do that, you need to see what the denominator is in factored form. Now the numerator is just 2x plus 3. And I guarantee you that they give you a function that looks like this, where you have like a regular x in the top and then a quadratic as an x squared in the bottom. What they're going to do is rig it so that one of the factors in the bottom will be this the same as one in the top. So in other words, 6x squared plus 7x minus 3. I'm pretty darn sure 2x plus 3 is going to be one of the factors. And how did I know that? Because it's in the top. Now, in order to figure out what this other factor is, when you FOIL this, 2x times this quantity right here has to give you 6x squared. So I'm thinking it's got to be 3x. Lastly, when you do the last terms, this guy times this guy has to give you negative 3. So that means this back number here has to be minus 1. And let's see if that works. If you were to FOIL that out, you're going to get 2x times 3x, which of course is 6x squared. When you do the outside terms, you're going to get minus 2x. When you do the inside terms, you're going to get 9x. And then 3 times negative 1 is negative 3. And sure enough, negative 2x plus 9x is the 7x we need. So there's our factored form. So it's really easy when I say find all points of discontinuity. I'm really just asking you to say what values of x make the denominator 0. Now it's really easy to see what makes the denominator 0. Either 2x plus 3 because of this guy over here. Either 2x plus 3 equals 0, which means 2x equals negative 3, which means x equals negative 3 halves. There's one point of discontinuity. or this guy here, 3x minus 1 could equal 0, which means 3x equals 1, which means x equals 1/3. So when they ask you find all points of discontinuity, what they're really asking is what values of x make the denominator 0. Piece of cake. Now, when they say I've identified the type of discontinuity, well, here's the thing. You learned in Algebra 2 that when you have a function like this that has, for example, 2x plus 3 over 2x plus 3 times 3x minus 1, you might have had a question that said, simplify this expression. And what you learned is you can cancel out common factors. So you'd cancel this out and cancel that out, and it would be equal to 1 over 3x minus 1. Well, being able to cancel out a common factor is what we would call a removable discontinuity. You literally removed it, you obliterated it by canceling it out, and now it's no longer a problem. So a removable discontinuity occurs at an x value where the common factor in the numerator and the denominator is. So removable should really be called maybe factor outable, because if you can, or cancel outable. So the removable one was the 2x plus 3, and that was when x was equal to negative 3/2. And the non-removable, which is the other type of discontinuity, I'm just going to write non-remove, that's going to happen at x equals 1/3, because after we cancel it out, we were left with this. And hey, you put a 1/3 in there for that x, you're going to be dividing by 0, and you're going to have a big blow up on the graph. So the non-removable one is 1/3. So very, very typical question as you're getting into the beginning of calculus for them to ask you, find the discontinuities and then tell me which ones are removable and which ones are non-removable. Well, the removable ones are the ones you can cancel. That would go away if you canceled them out, the common factors, and non-removables are the one that don't. Real easy. Lastly, where is it continuous? Well, the answer here is simple. It's everywhere except these two numbers, okay? So if you think of a number line and go, all right, on a number line, negative 3/2 would be over here, and 1/3 would be here. Those are the only places where there's going to be a break in the graph. There's going to be a discontinuity at both of these. So that means we're going to be continuous here. We're going to skip over and be continuous here, and we're going to skip over and be continuous there. So the intervals where we're continuous is negative infinity to negative 3/2, joined up with this stuff between here, which is negative 3/2 to 1/3, joined up with this stuff over here, which is 1/3 to positive infinity. So there's your type of question. Super, super easy, as long as you get those basic ideas and you understand the vocab, as long as you can factor, which is a thing. So the hint there, though, is if they give you one of these things like a 2x plus 3 in the top, you can almost bet your life that one of the factors in the bottom will be that same factor, and it kind of helps you with the process there. So here's that same question as the last one, only asked in a different format. So it says, again, they give you some function here, and they say find the discontinuities, identify the type of discontinuities, and then state the intervals where it's continuous. Now, I just told you in the last thing that where you find the discontinuities, that was like where the denominator equals 0. Well, in a piecewise function, one of these things where it's defined in pieces, the discontinuities, there's no denominator here, so the discontinuities are going to occur only at these, what I call the border points. So in other words, this function is going to do one thing for x's that are less than negative 2, and then it's going to follow this rule for x's greater than negative 2, greater than or equal to negative 2. And so here's the deal. This part is not going to have any breaks in it. It's going to be 5 minus x squared. It's going to be like a parabola sort of thing, and it's just going to be doing its thing. And then we have to find out what's going to happen at this magic border point, at this negative 2. Is the parabola that's going to be here, which is going to kind of look like this. And again, you don't really need to know what this is going to look like. That parabola that's going to leave you like that. What's going to happen when this rule kicks over here and becomes this different parabola? Who knows? Maybe that one looks like this, where they meet up. Or maybe, it is somewhere else, and there's going to be this giant jump in y values between these two things. If those two things meet up right here, then there's no discontinuity. The function's fine. Then where this guy leaves off, this one picks up and it goes on its way. Or this guy's going to leave you off somewhere, and then you're going to have to jump to some y value and go on your way, and then there's going to be a discontinuity. So the only thing we have to do is check and see what happens here at -2. So if we plug -2 into the top function, we get 5 minus -2 squared, which is 5 minus 4, which is 1. So that means this blue function is going to leave you off here really close to x equals 1. It actually has an open circle there because it doesn't include the equal sign, but it's going to leave you off very close to y equals 1. Now, to find out where the red guy is going to pick up, where this guy is going to pick up, plug -2 in there. -2 squared plus 5 times -2 minus 3. And we get 4 minus 10 minus 3, which is what, -9? So this red guy is going to pick up way down here at -9 and start doing its parabola thing. So there's this giant disconnect between where this guy left you off at 1 and where this guy picks up at -9. And so that's going to be a discontinuity. It's going to be a break in the graph. The graph goes up like this, and then it goes down and does its thing from there. That is a discontinuity. There's a break in the graph. So the only discontinuity that occurs is at x equals -2, and that is a non-removable. Graphically, non-removable discontinuities are like when you have a big break where it's got to jump from one value to the other one. Removable discontinuities would show up as something like this. They show up as a hole. They might go like this, then you have this little break in the graph, and then it picks up from there again. That would be a removable one. It's unlikely, I would say, that a teacher would give you a removable discontinuity in one of these kind of piecewise functions. So basically the thing to do here is check the x value in this piece and check it in that piece, and if they don't agree with each other, it's a discontinuity. So we're going to say discontinuity at x equals 2. There's our first answer. It is non-removable because we have a big jump in the y values. And then lastly, where is the function continuous? Well, it's continuous everywhere except where it's discontinuous. So for part 3, we're going to say it's continuous as long as we are from -infinity to -2, and then -2 to +infinity. So again, number line, here's -2 here. The function's fine here. It skips over -2, and then the function's fine there. And there she goes.